Good morning, good afternoon, and good evening. Thank you for joining us. My name is Whitney, and welcome to our webinar introducing the Arista 7170 series multifunction programmable network switches. I am pleased to introduce our first speaker, Martin Hall, Associate Vice President of Cloud Titans and Platform Product Management.
Hello. So on today's Arista 7170 series webinar, we're going to be covering a number of different subjects. We're going to start off by covering introduction to what are the Arista programmable platforms, what are programmable platforms generally. We'll be looking at a series of target applications, and then we're going to switch and kind of do a more detailed product overview, look at the architecture of the 7170 series, and then finally we're going to give a summary, if you will, of the benefits and the advantages that the 7170 series brings. So first of all, let's take a look at what is the state of the art of both non-programmable and programmable solutions today. In many large scale networks today, there's a series of networking problems that are typically solved by adding routers and more networking tiers to solve those problems. If you're trying to address challenges with NAT, traffic filtering, scaling up tunneling, tunnel terminations, you add in tiers of additional devices. That in turn brings additional cost. It adds latency to every flow that's got to go to these external devices and then come back into the network. And as you need to add capacity, that itself is costly and complex. Solutions themselves are relatively inflexible. Every time you want to add in a new protocol or a new feature set, that can require a wholesale rip and replace. Examples of this are in the areas of virtualization, network overlay technology, implementation of new routing protocols, or segmentation. So segment routing, VXLAN, QUIC, or something as simple as MPLS over GRE. Those can be areas where wanting to add those into your network requires you to go out and procure and deploy a new network technology. There are alternatives. Those alternatives can often be delivered in the form of a server. A server is very flexible in that you can run a series of software solutions, but the server's performance is limited by the I/O and the memory footprint, or the CPU and the memory footprint. Anytime that you want to add more additional networking services, you turn another virtualization offering on, which in itself gives you the capability but also loads up that CPU. So whether that's through, again, network address translation and more segmentations or monitoring technologies, each one of those is an additional piece of work that's running on the CPU. So a way to address that would be the implementation of an intelligent offload engine, a smart NIC. That smart NIC takes the load off the CPU and accelerates it on dedicated hardware. But again, it's an additional cost, and it's another level of complexity added to those servers. And in their own way, a smart NIC doesn't necessarily scale beyond being deployed in that single device. You have to have a smart NIC per server. So it's another device that's relatively flexible and programmable is a network appliance. But many of the network appliances out there today are essentially single function. So every time you need a new type of device, you have to go out and identify the best of breed supplier, bring them in, and each one of those brings a new operational model. There's a different support model, there's different operations, and you don't get good reusability across different functions. And we've often seen with a lot of these network appliances that as you want to add capacity or you want to turn a new feature or functionality on, there are costly software licenses to do that. So another way of looking at the evolution of these programmable platforms is starting with the x86. The x86 server today is a multi-core high-performance machine that has got the most flexible architecture. You can run any combination of software on that CPU. What we've done is we've seen the evolution to a set of programmable intelligent network interface cards, where through some I/O acceleration capabilities we've got higher throughput and higher performance. And if you kind of look at that and extract the benefits of that and see how can we leverage that into a programmable switch, you end up with effectively a smart switch, where it's possible to take a series of these network critical functions and embed them back into the network itself of both the aggregation tier and the leaf tier. So not only offloading the x86 to an intelligent NIC, but now offloading the intelligent NIC into the programmable smart switch. Over the last few years, we've seen the introduction of a number of programmable packet processors. So we look at the Arista portfolio today. We have our 7050X3 series, we have the 7160 series, and now with the introduction of the 7170 series, we have a third set in our programmable packet processors. Each of the chipsets on these, the Trident 3, the Cavium XP80s, and the Barefoot Tofino, are programmable. They all have elements of programmability built into them. They have the capability to add new protocols, add new features, and reallocate the logical resources within those chipsets to be leveraged for larger or smaller layer 2 and layer 3 scale. What's different about the Arista 7170 series, based on the Barefoot Tofino chipset, is it's the most flexible. It is a completely programmable packet processor. Our software engineering team has to make the decisions on which logical operation to perform in each of the lookup stages. There's no predefined order of operations. We get to choose the lookup type, the size of the tables, the outcome of those lookup operations. So as networks evolve, we can add in new capabilities, we can change the scale, and we can take functionality that's not typically being delivered on a fixed configuration form factor or a fixed pipeline and deliver that on the 7170 series. And what's also unique and different about the 7170 series is how you get to those programmable features. So our software engineering teams, the merchant silicon engineering teams, can add new features to functionality, but you, the customers yourselves, can also play a part in how do you get access to these new programmable chipsets. So through the P4 language, you can get a capability to add control, add functionality into a chipset, into the system that you've deployed in your network. So let's take a closer look at the 7170 series themselves. We're introducing two new products. We're introducing a 2RU 64-port 100 gig system and a 1RU 32-port 100 gig system. The 2RU is available now, it's shipping. The 1RU is a little bit later in terms of release. It'll be available in about a month's time, towards the end of July into early August, and is supported on our next major software release. Both of these systems are dense, 100 gig and programmable, and can be used at the spine or the leaf of the network depending on your requirements. Both of them are using the same Tofino programmable chipset at the heart, and they can support up to 5 billion packets a second forwarding capacity with a fully shared 22 megabyte packet buffer. Based on cut-through forwarding, we're getting sub-microsecond latency. Clearly there's always going to be some features you can turn on that will get that latency a little bit higher, and also there's ways to get the latency a little bit lower. They're optimized for regular data center deployment in that they are fixed configuration with multiple power supplies and fans, so they're highly available. They have back to front and front to back airflow, and power is under 5 watts per port on a typical basis. That again will vary depending on which optics and cables you choose to plug into these. So where they get interesting is the data plane tables, flexible not only in their size but in the functionality. And they have support for advanced encapsulation, tunneling and segmentation technologies. And that is delivered through the programmable pipeline, which allows you, the customers, to turn on or enable a flexible set of features and scale, which you'll see we deliver through something called a profile. We'll get to that in a little while. So we have a flexible pipeline which we can deliver a rich set of features in combination to enable a series of custom applications. So let's look at some of those custom applications. So we're calling the 7170 series a multifunction programmable platform. It's a bit of a mouthful, but that really tries to encapsulate what we think this system can deliver. And that is that it is a platform that can be deployed in many places in your data center networks today, delivering a unique set of features and functionality that can't be delivered on traditional layer 2 and layer 3 switches. So we have support for large tunnel scale, embedded application telemetry with deep visibility, high performance and flexible routing capability, and then we have a set of security and network address translation capabilities in combination with large scale ACLs. So these are just some of the ideas or some of the flavors of the capabilities that can be enabled with the 7170 series. And some of these are taking features and functionality that are possible on some of the other systems, but increasing the scale, or doing it in a way or a level of performance that isn't necessarily possible on the other systems. So let's take a look at the network tunneling example here. So the first thing to call out is just scale. 192K tunnels on a single system, a single 1RU or 2RU system with almost 200,000 tunnels. At the same time, 5 billion packets a second and 6400 gig ports. So there's a number of systems out there today that are deployed for large-scale tunnels. But to my knowledge, those tend to be high-end router systems, modular routers with relatively low density with this scale. Or if you want the density, the scale comes down. So we have the flexibility within the 7170 series to support a number of different tunnel encapsulations or tunnel types, varying from MPLS over GRE, MPLS over UDP, VXLAN. So one example of this we have been working with a customer on is the ability to bring in an MPLS environment, terminate those MPLS tunnels on the 7170, and then translate them back to a series of VXLAN tunnels. Doing this at a relatively low scale is possible on many devices, but scaling it up to the level of performance and level of tunnels here is unique and custom to the 7170 series. So the other use case then is application telemetry or integrated network telemetry. So we have the ability within the packet pipeline to look within the packet headers and to look for the packet types, the protocol types, any field you can find within the first 128 bytes. And then we've got the information on that. We can take the information on the flows, on the packets, and stream them off the system clearly in real time. So you're getting, if you will, S-flow-like information on every single flow inside the system. So you get a high volume of visibility without adding to the CPU loads. What you're getting off the system is information rich, and we can use intelligent triggers. We can monitor the queue activity, the depth of the queues, how long a packet was waiting in that queue. We can report based on what was the classification based on QoS. Did you get dropped? Why did you get dropped? And any other custom field that you can identify within that first 128 bytes can be triggered on, accounted for, and put into the telemetry packets that are sent off the box. So two other use cases are examples of scale. So a large-scale ACL or a large-scale NAT profile. So a large-scale ACL is taking regular ACL policies but scaling them up to, in this case, over 100K, but also having the additional capabilities to be reflexive and stateful and to support nested or hierarchical and conditional ACLs. So as traffic's coming into a system, you can make a series of stepwise decisions as to whether or not that traffic gets forwarded onto the next hop and out of the box. From a NAT perspective, we've seen many environments today where service providers, carriers have got NAT deployed at multiple entry and exit points to their private and public networks. Those environments are transitioning away from traditional telco type systems to more programmable fixed form factor devices, and we see the 7170 playing a role in those NAT deployments. So we will have a broad set of NAT features, effectively similar to where we are today on the Arista 7150S series, with the advantage of it's a higher performance, higher density system with additional scale. So over 100,000 NAT sessions on a 7170-64 and about 200,000 on the 7170-32. So the final use case I want to kind of draw attention to here is something that, again, we find particularly interesting, and that is the transition from hypervisor, virtual switch, virtual machine environments for virtualized workloads, moving to a bare metal deployment model where you, the customer, get full control of the compute node. But the multi-tenant hosting provider still needs to deploy a range of services that protect, encompass, and give you the value add on top of your bare metal deployment. So there's a couple of ways to approach that, and that is to deploy additional compute nodes to run these value add services, to deploy a series of appliances, and every packet, all the traffic has got to go into and out of the series of appliances. Or we can take these intelligent services that would normally run in a vSwitch and run them directly on the top of rack first hop leaf switch, in this case the 7170. So the set of features we can run is network security with algo match, scaling up to 40k entries. We can do that at the same time as turning on VXLAN and having 100,000 VTEPs or tunnels. We can also turn on network address translation, so you've got private dedicated customer networks with 8k entries. And then from a segmentation perspective, support for up to 128 VRFs. And doing this, all of these features, at the same time that we have VXLAN with an IPv6 underlay and a full routing stack with ECMP, so BGP or OSFP based. So a full routing topology, overlays and underlays with these rich feature combinations running on top of that. So what we're doing here is we're avoiding the need to send all the traffic into separate devices, which saves space, power, capex and opex. It simplifies the operations, it simplifies the troubleshooting, means you can have a consistent set of services in any rack. So as we think about how these solutions and use cases align to the different customer verticals, everything from the enterprise customers and financial services all the way across to a telco or a service provider customer has got some level of interest in each one of these different use cases, and in many cases in combinations or multiples of them. So we're very excited about the new markets and opportunities that the 7170 is going to open up, and the ways in which customers are going to come and talk to us and ask us about additional capabilities, additional use cases that we can enable through the Arista 7170 series. So with that, I'm now going to hand over to Simon Capper. Simon's part of our engineering team, and he's going to give you a more in-depth overview of the platform and the architecture of the Barefoot to Fino chipset inside the 7170 series.
Thank you, Martin, for that wonderful introduction. We'll go into the technical details of the 7170 series now. The 7170 series is a high-performance 100 gig platform. It comes with a 64-port or a 32-port configuration, and in both cases we use the same Tofino ASIC inside from Barefoot. The Tofino, as Martin's mentioned, is a very, very programmable pipeline, and we've come up with a product here that's basically optimized for data centers. The core of this switch is the Tofino packet processor, and I'll go into some of the details about how it works and how we use it to develop a switch using EOS. Tofino is a single chip, a system-on-a-chip ASIC, and it consists of 256 25 gig SerDes, which can also support 10, 25, 40 and 50 gig and 100 gig ports, and can completely break out into 256 individual ports or 64 ports running at 100 or 40 gig, and it supports a 22 megabyte packet buffer. We've spent a lot of time in the engineering team fully understanding how the chip works, and have basically written our own custom programs to manage the resources inside the silicon. The chip basically consists of highly programmable match action engines and tables, which utilize TCAMs and SRAM resources that in the ASIC. The chip is broken up into 4 pipelines, and within each pipeline you have a set of MACs that share a set of common resources. Packets arrive at one of the ingress MACs and then progress through the pipeline through each of the match action stages in that pipeline. During pipeline processing, the packet is rewritten and modified, and the actions that are performed on the packet are determined by these match action stages in the pipeline. And eventually all the packets will pass through the ingress pipeline and then the egress pipeline, and will be rewritten and retransmitted. Let's talk about how the packets are processed by the pipeline. The first stage is the parser. This analyzes the packet, breaks it up into the various headers, and puts the headers into a data structure in the chip called a PHV, or packet header vector. This is a series of bits which are available in every stage of the chip and allow us to basically do lookups on any header field in the chip. So for instance, we could look up on the SIP in the outer header at any point in the chip, because the parser puts those bits into the PHV values. So once the parser's broken the packet up into the various headers, it goes through each of the 12 match action units inside the pipeline. There's 12 on ingress and 12 on egress. In between the ingress and egress stages is the queuing system in the chip. Each match action unit can consist up to 12 tables, and each table can take its keys, its input keys, from the PHVs. Each table has a set of actions associated with it, and parameters perhaps, and based on which row in the table hits, if any, the table will rewrite additional PHV values in the pipeline. So for instance, the route lookup could write a next hop table pointer, and that PHV pointer would be then used by a subsequent stage in the chip to actually look up the rewrite information for a packet. For instance, in a routing case, you would rewrite the destination MAC address and the source MAC address on the packet. If a table has a miss, there's no action found, there are ways for us to configure default actions. For instance, in the case of a MAC address missing, there may be a flood action as a default action on a table, so the packet gets flooded to all members of a VLAN. The output of a table can be written into a PHV and passed down the pipeline to another match table. This allows us to chain tables together to form a single set of actions to be performed on the packet. Once the packet has passed through all the match action units, the deparser reassembles the packet for retransmission. The reassembly depends on the values of the PHV fields that were written by the various match action units in the pipeline. So for instance, if we've modified the DMAC of a packet, the deparser will reassemble the packet with the new DMAC value. The Tofino program that has been developed by Arista integrates seamlessly with the platform-independent code in EOS. This means that features such as routing, bridging, ACLs, QoS, mirroring work in the same way on Tofino as they do on any other ASIC. The single API, single interface to EOS can be used to configure the features that are the same on Tofino as they are on any other platform. EOS is basically still EOS. You don't have to change the way you use EOS to use the 7170. However, in order to utilize the flexibility of Tofino, we've actually created a chip or a platform with multiple personalities. Additional commands have been added to EOS to allow you to pick a profile that gets used to run the chip. The profile defines which features are available in the chip and at what scale they run. So for instance, you could have a profile that was designed to run large-scale layer 3 networks, or as Martin said earlier, we have a very large-scale tunneling profile. We also have profiles with large layer 2 tables in. It's not possible to have every feature available all the time on any ASIC, but what we can get on the Tofino, on the 7170, is a platform where you can, as a customer, can choose which features you need and which features you need at which scale, and basically pick that combination of features to run in your network. And you do not need to use chip resources for features that are not necessary in your network, allowing you to kind of maximize the use of the memory available in the chip. When deciding how to add a custom feature to the 7170, customers really need to decide what kind of engagement model they need to pick. I've already mentioned the two models. Either you come to us to work with you on building the feature, or you do it yourself. One of the advantages Arista brings to the table here in the engagement model where you bring the feature to us is that we have many hundreds of man-years of experience working with ASICs in general, and in particular with the Tofino chip itself. We have a lot of experience developing programs over the last several years, and this allows us to optimize and develop programs in a way that would be very difficult for a layperson or someone new to this kind of technology. Developing a P4 program is more like writing an FPGA image than writing a software program. The chip has a very, very tightly set constrained set of resources, and the program itself runs as a single image, unlike a modern operating system where you have several programs running independently from each other, and they don't really interfere with each other. Inside the ASIC, the program has all the tables in the program have to work as a single unit together. So changing one table can have an effect on another completely unrelated feature in the chip. If you decide to do your own full custom implementation, you'll have to understand all of these implications yourself and work with and actually learn how to manage the resources in the chip. There are over a dozen different constraints in the chip, different types of resources, which you have to consider when writing a program. And when you're trying to get a program up to a large scale with large table sizes, understanding all those constraints and how to work around them is critical in getting the most out of the hardware. The Tofino is a very capable chip, but just like any other FPGA programming, it's quite a challenge to become going from a layperson to an expert in programming the hardware. We get a very significant percentage of the resources fully utilized in our profiles, which is how we managed to get to 192K tunnel support in one of our profiles. A layperson using a naive programming model may only be able to get to 20 or 30,000 tunnels. So I would encourage people to approach us first before thinking about going to their own full custom implementation, as we will be able to give you a much richer solution which not only will scale better with other features, but will also integrate better with EOS itself, so that you won't have to develop your own routing stack and other basic network functions that you would otherwise have to develop yourself. Developing a full networking stack on a switch is a very significant undertaking, and as Arista has done so, it's taken us over 10 years to get to the point where EOS is now, and doing that yourself would be a very significant effort. And at this point, I'm going to hand you back over to Martin.
Thanks, Simon. I certainly find that any conversation about what happens inside the packet processor to be very revealing, and I think that was very, very clear for most of the people out there. So with that, going back to kind of thinking about the 7170 as a system and how it can be deployed in your environments today, there's a number of advantages or benefits that get derived on the 7170 series. And at a high level, this system is capable of delivering far greater performance than traditional middle-of-the-network devices and appliances. It allows customers to replace a series of complex routers which might be being deployed for a single function, something such as NAT or traffic filtering, where you probably not only got the cost of the base system, but also a series of expensive feature licenses overlaid on top. And then the third primary use case, I think, is for customers who are contemplating or have already deployed a smart NIC technology and looking at how you can either avoid deploying that smart NIC or to preserving the precious server or hypervisor resources by offloading some of the functionality into the first hop switch. So to take a closer look at some of those kinds of use cases, we've got Chaitanya here with us today, who's going to walk you through the comparisons that we see between those existing solutions and what the alternatives are.
Thank you, Martin. A good way to think about the richness of the 7170 series is to understand the range of problems we're tackling and compare to the set of alternative solutions that are available today. Here are three classes of products: complex routers, dedicated smart NICs, and hardware appliances. With a throughput of 12.8 terabit per second and a programmable pipeline, the 7170 series provides a high performance, lower cost, and lower power alternative to the single function solutions provided by the expensive router platforms, with the services modules and complex licensing models. In addition, the 7170 series allows for a whole new set of capabilities in the switch that previously took place in a host, a VM, or in a SmartNIC. These approaches have limitations, ranging from using up the precious CPU and memory cycles and building complex and localized solutions. Often, using a dedicated network appliance in such situations does not always scale and can result in creating performance bottlenecks, adding more hops in the network, and increasing the latency. In comparison, the 7170 series allows embedding the network critical services back in the leaf and spine of the network, avoiding the need for more devices and hairpinning of the traffic, and eliminating additional hops and latency. Let me summarize the advantages of the 7170 series. It supports multiple solutions on a single platform with high performance. Multiple profiles are available, and moving between profiles is simple with no complex qualifications or hardware changes. The 7170 allows customers to achieve the benefits of server workload acceleration or to replace routers that are being used for service acceleration or tunnel scaling. The 7170 is a simpler solution for increasing performance, comes with consistent operational models, and does not force additional licensing complexity. It also allows customers to extend the life cycle on servers, avoiding new purchases and accelerating new applications and services. Now, let's look at how the 7170 series fits in the Arista portfolio. As Martin covered earlier, the 7170 series currently offers a choice of two products. The 2RU 64-port 100 gig switch can be compared with the Arista 7260 CX3 that has the same port count. The 7260 X3 series continues to be the Arista's high volume offering for scalable spine and leaf deployments with a broad range of layer 2 and layer 3 features, including UFT for scaling resources to up to 256,000 V4 addresses, which is more than sufficient for regular deployments. The programmability of the 7170 series complements the 7260 X3 and enables additional functions for tunnel scaling and specialized security roles, solving unique network requirements. While it is a scalable platform, it is still power efficient and high performance, with latency under a microsecond. Similarly, the 32-port 7170 is comparable to the 7060 X2 or 7050 X3 series, which offers 32 ports of 100 gig in 1RU form factors. All these products support a broad range of speeds, making them ideal for high-density leaf and spine deployments. Where the 7170 adds additional capability is the support for programmable profiles, enabling large-scale NAT, tunnels, and advanced network telemetry that are applicable to many large enterprises and service provider environments. Now, as all the Arista products come with a single EOS image, it's a simple matter to run any of these with a single software version in a common operational model, allowing faster deployment no matter which models you select.
It looks like we have a few questions rolling in. Let's take time now to answer a few of those.
Okay.
How easy is it for a novice to program in P4, and how does that compare to C++?
P4 is a completely different language than C++. Certainly having general programming skills will help you understand P4, but an expert C++ programmer will be a novice programming in P4 and will have to spend a significant amount of time getting to the point where they can program proficiently in P4 to get the most out of the hardware.
Okay, next one. Can we load P4 code for a SmartNIC onto the 7170?
No, the P4 program needs to be compiled with the target-specific compiler. It's quite likely that the resources available in a SmartNIC are going to be different than those in the 7170, and there's no guarantee the program is going to fit correctly.
Can the 7170 be used as an L4 load balancer? What are the limitations?
Yes, with the right P4 program, absolutely it can be used as a load balancer. The biggest limitation would be detailed flow tracking. There are ways to get around that, but the memory in the chip has a limit, and the number of flows would be limited. Significantly, it would be significantly fewer flows could be tracked than in an x86 based flow tracker.
Okay. If EOS is running as a control plane, what's the P4 based code doing?
The P4 based code itself is actually in the ASIC. It's a series of register programming in the chip. The P4 code is basically running the data plane.
Okay. Can the 7170 support internet scale route tables?
Yes, but you'd have to compromise the pipeline. The amount of memory required to fit the full routing table is significant, and it would compromise other features inside the chip to the point where it's debatable whether the switch would work in a useful fashion.
With the 7170 offering additional programmability, does it consume more or less power than the 7060X series? So that's a good question. The fact is that the 7170 64 by 100 gig actually requires less power than the equivalent 7260 CX3, even with the additional programmability. Now on the one IU, there's a number of comparable systems. Chaitanya took you through one of those, both the 7060X and 7050X, and for each of these the power varies by less than 1 watt per port on a typical power basis. Fundamentally, there's no significant power penalty for the additional programmability. Of course, there will always be a number of other factors that help you decide what it is, but I wouldn't say that power is the biggest factor there. Then what is the availability of the 7170s? So the 64-port 7170 is shipping now and is supported in the latest version of EOS software. The 32-port model will be available to ship in about a month, 6 weeks time, and will be supported fully in the next mainline version of EOS that's due out around about that time.
That is all the time we have. Thank you so much for joining us today. If we did not get to your question, please feel free to email us at webinars@arista.com. A recording of this webinar will be available on our website.